Sorry for that. All right, so the next thing I want to talk about is dynamic priors. So this is priors where we now have actual masses and forces acting on masses. And again, they're actually going to come from this notion of continuum mechanics. And so in particular, let's look at these equations again. So basically the same fundamental insight that basically the change of that we have in this, if we have some kind of a property that's described in the material space, it is related to spatial and temporal gradients in the real world. Okay, and so what we can do is, so this, as I said, mentioned before, this holds both for scalar fields and for vector fields, and in particular, it holds for the velocity field itself. So if we put the velocity field into this equation here, we get this relationship where the velocity in the material space is related to space and time derivatives in the spatial of the velocity field in the spatial domain. And now, what kind of priors can we, if we think back to physics, what kind of conservation laws do we have in mechanics? Well, one of them is actually conservation of momentum. Okay, momentum means that basically things tend to keep going in the same direction that they were going in before, at least in the absence of external forces such as friction. Okay, so now if we go to something like a fluid, this would mean that we would have a fluid where the viscosity is negligible, for example. Then we can say in our material space, the velocity would tend to be, the time derivative of the velocity would tend to be 0. And again, we can basically have now an equation that looks exactly like what we had before, just with the velocity field, okay, instead of the scalar quantity. And so the implication of this is that as we evolve our fluid, the velocity field should basically be carried forward by itself. So if I have a velocity field at a certain time, and then I look at it at the time t plus delta t, the velocity at the new point should basically be the velocity of the old point, just moved forward by itself. So this is called the self-advection of the velocity field. So the velocity field basically warps itself into the new velocity field. Okay, so now the self-advection property is often combined with incompressibility, which is what we will also talk about in just a second. But let's think about what other priors we might have from physics. So we know conservation laws like conservation of mass or conservation of mass density. Now the problem is that this is directly not very easy to express because oftentimes with most of the imaging methods we're talking about here, we don't observe these quantities directly, right? We can only regularize something that we somehow observe or at least can infer indirectly. And so, but one prior that we can put in is the notion of incompressibility. Now, this is now not a general prior, but it is a prior for fluids, for a lot of fluids. So that basically the volume of the fluid is preserved not just globally, but even locally in a local spatial neighborhood. And in fact, so I'm not going to go through the derivation, but basically this incompressibility is basically related to the divergence of the velocity field. And so if the divergence of the velocity field is 0 everywhere, then it means it's an incompressible fluid. And so we basically have two ways of using this information. There's one very straightforward way, which is to just take the divergence, which is a linear operator, and just add it as a regularization term to your optimization with like a least square penalty. And then this will basically be a soft constraint where you say, okay, my fluid is mostly incompressible, and it will tend to be incompressible. And so in many cases, this is something that holds even for incompressible fluid, because it's not a hard constraint. Okay, even compressible fluids will tend to have a lot of regions which are actually not compressing. So that's why it works even in a very, very general setting. However, there's also a way to actually use it as a hard constraint. And basically this hard constraint, this approach is based on the so-called Helmholtz decomposition, which basically says that if you have any kind of vector field, you can compose it into two parts. One which is curl-free or solenoidal, and one which is sorry, a solenoidal one, which is the divergence-free one, and then a curl-free one. Okay, so basically we can decompose our fluid into a curl-free one and a divergence-free one, and the curl-free one actually moreover can be described as the gradient of some kind of scalar field. And and this scalar field, we don't know yet what it is. I'll give you some physical intuition about that later. But basically, what it means is we can just basically compute the curl-free field and subtract it out from our arbitrary flow field and get our incompressible our volume preserving flow. Okay, and this can actually be expressed as a proximal operator. So it actually is very easy to integrate into any kind of optimization problem. Okay. So let me just let me just fast forward through some of this. Let me just maybe skip straight to the how we actually put this together. Okay, so basically the key here is that so there is actually a physical interpretation for this, which is that I think it would take too long to go through this, so I think I'm going to fast forward. I'm just going to show you the optimization problem actually in the end. Okay, sorry for that. All right, so basically, by putting this kind of incompressibility in, we basically have now the following optimization problem, which is an extension of what we've seen before. So again, we have our data term. We have flow consistency, which is basically the Horn-Schunck optical flow style term that we've seen before. We have smoothness terms for the flow. We have now the self-advection property, where again, we say that if we take the flow field and we advect it forward in time, it should be consistent with the flow field that we observe there. But also the same thing holds backward. So if we take the flow field and backward advect it to the previous time step, it should also be consistent with that. And then finally, we have a projection operator that gives us this divergence-free flow. And sorry, I mean, I have the slides, but I think it would just take too long to introduce you to how this projection operator is actually computed. But basically, it is very similar to a step that we use in fluid simulation. So it's basically a partial fluid simulation step that we put in as a regularizer for our reconstruction problem. And so this is the optimization problem. Again, we can split it into alternating, solving for the volumes or the data and the flow fields, and then solve this with any kind of numerical optimization problems. We usually use proximal methods to solve these kinds of problems. Now, the idea is, so a lot of this stuff holds not only for fluids, but fluids are by far the most, common application for this kind of stuff, because incompressibility, it does not really hold for objects with rigid bodies and things like that. So we are looking mostly at fluids if we talk about these types of priors. Now, okay, so let me just show you some examples of how this can be used now. So the one problem that that's happening in scientific imaging a lot is that people want to do seed flows with particles, and then they want to image or understand the 3D flow by tracking these particles. And oftentimes this is done in 2D. So here's a conventional what's called particle imaging velocimetry setup. So basically, you have a volume with the particles and the flow here. You do a laser sheet illumination of this, and then basically that highlights only the particles that are in this 2D slice, and then you have a camera that actually observes the slice, and then you do tracking to basically observe the motion, get the flow field of this of the particles. Now the problem is that we only have a 2D slice of the volume, and we only get 2D motion because we can only track in plane. In fact, this method is actually useless if you have 3D motion, because you cannot track particles at all anymore. The particles will just come in and out of the plane, and you can no longer track them. So one of the ways you can solve this is with many cameras, but that has actually a lot of practical issues. An alternative that we came up with a couple years ago was actually to do a rainbow illumination. Okay, so here we call this rainbow PIV. So the idea here is that you don't have, a single sheet illuminated, but you have basically a rainbow of monochromatic light, basically illuminating the whole volume. So basically the objects that are far away, the particles that are far away, they would be blue. The particles that are close would be red. And then basically you have a color coding of the depth, basically. This has also the nice advantage that you can actually design diffractive optics that you just put on front of your camera to actually keep everything simultaneously in focus, because focus is always a problem for these kind of PIV setups in 3D. But then we basically have an image formation model where we can relate the color to a 3D position and then try to do tracking that way. Now, the image formation model is actually very similar to what we've seen. So we end up with an all-in-focus image like this, and we want to actually extract the particle locations and then track them over time. Now the problem is basically, so we're going to take this volume and represent it as a volume of occupancy probabilities. So every voxel has a certain probability that there's actually a particle inside, and then now we're trying to solve optimize this occupancy probability volume. But the problem is that our inverse problem here is actually very poorly conditioned, because the color is very low frequency information. We don't get a lot of detailed set resolution with this kind of approach. And so actually, when we just do this without temporal priors, without any kind of additional priors, these are roughly the volumes that we expect, right? So for every XY position, we have like a smeared out probability of where the particle actually is, and this gives us this is really not good enough to be useful, really. So now by taking what we already saw and basically putting the temporal priors in, we can now enforce the physics between the time steps, and actually that allows us to have much better localization in the set direction of these particles. There's an extra term here, which basically, actually two extra terms. One which basically says that here we have particles that are sparse in the volume. So we can just say that the volume occupancy, these probabilities, they should be sparse. And then the second thing is that they're really probabilities, so that they should be between 0 and 1. And that's a convex projection also, so that it all fits nicely into a convex optimization kind of framework. And where's my slide? Okay, now I don't have this. Now I don't have, sorry, I don't have the slide for the showing the result. Okay, the same kind of principle though can be applied to other, other kind of imaging modalities. So here's, we did a lot of work on these kinds of reconstruction problems with, partners at KAUST and in other places that are coming from the sciences and that want to actually image certain phenomena. So here's a setup from suit imaging. So basically this is a combustion research. There's a combustion chamber. We're trying to do tomographic reconstruction of basically the suit plume from just 3 cameras. And again, this is so underdetermined that really without additional priors, it's basically hopeless. And we, these kind of methods that I discussed help for that as well. Next up, we have holographic particle imaging velocimetry. This is similar to the rainbow PIV, but now we have a holographic image formation model. Again, the XY resolution of the holographic particle localization is actually very good, but in SET, it's not very good. And so again, these priors, the same kind of priors I talked about before, they're actually useful for that. And then here you can actually now see a recovered 3D flow from this kind of imaging methodology. Finally, we worked on things like background-oriented Schlieren. So this is another computational imaging method for, observing transparent flows in this case. So we don't want to, we don't have the ability to see the flow with particles. This is just an airflow. And basically what happens is here that the flow, what happens is that there's a refractive index difference that causes the light to bend. So this is actually related to the phase imaging that Laura was talking about. But basically the way we solve it here is now that we actually have a patterned background plane here. And then we have a reference image that's undistorted, and we have a distorted image. And we can actually compute the 2D optical flow to actually give us information about this gas volume. And then we can take that and track it in 3D. And so here's basically the, I find this very fascinating. So this is actually a video, even though I'm sure you will not be able to see anything, but this is actually a video. So visually, it is not, the information is just not there. But if you just compute 2D optical flow and visualize the optical flow with a color map, you get this information. You start understanding a little bit. And then it actually turns out physically that this 2D flow here is actually the gradient of the phase, the optical phase that Laura was talking about. And so actually, if we integrate this, then we actually get this kind of plume in 2D. And in fact, we can do 3D tomography on this if we have multiple cameras and do 3D reconstructions and track in time with what we've discussed today. Okay, so in summary, basically we have pretty much a framework here now for imaging any kind of moving target with these types of motion priors. There are 2 types of motion priors that are that apply depending on what you want to image. One is a kinematic prior, which basically just says this fundamental consistency information that you can put into your reconstruction problem. And then more generally, you can have dynamic priors if the phenomena you're trying to observe has certain extra properties. So this is really information that you need to decide whether it holds for you or not. Now, I showed specific examples today, like tomography, like these fluid imaging problems, but in fact, it really applies across the board. for a large number of inverse problems that are ill-posed and where we can pool information across time to make our problem much better conditioned. Now, one thing, of course, what you've seen in this talk is that there was a notable lack of deep learning in this talk. And in fact, we are working on deep learning, but actually the question is, how do you take these kind of physical priors and actually combine them with deep learning kind of approaches? So you could try to learn the priors, but that requires a lot of data, which typically in scientific imaging, you don't have the variety of data. And you also don't want to overfit to, you know, if you want to image a phenomenon, you may want to make sure you don't overfit to a model that you have, which may not be that accurate. You know, because I mean, if you fully understood the phenomena, there wouldn't be a need to image it in the first place. So there's sort of this question: do we really want to have learned kind of priors instead of the physical priors? But actually, another avenue would be to actually take these physical priors and integrate them with learned reconstruction, where the learned reconstruction is just responsible for the spatial aspects of things, where it has been shown to work exceedingly well. So this is ongoing work, and you know, I'm sure there will be great work coming out in those directions. So thank you. Sorry for the issues with the slides and everything. There's somebody at the mic already, but you can be next. Yeah.
Hi, I'm Kilju from Reality Labs at Mata. I thank you for the great talk. I love the idea of using computer tomography for the computer vision and graphics applications. So.
Maybe I'll just step down.
Okay. Is it better now, or is it better? Okay. Thank you so much for the great talk. I love the idea of using CT technologies for computer vision and graphics applications. And you showed a very nice slide of the mapping at the beginning of the talk, the mapping between material space and the Euclidean space. And you can link the data between the two spaces. But in the Fourier optimization framework, if my understanding is correct, there's no mapping from the material space to the Euclidean space, but instead there is a per frame density field and per frame velocity estimation. So there's no concept of a canonical model or material space model, but instead there is a just a per frame derivative of the field. So
okay, yeah. So basically, you're referring to the fact that we don't really have a material space in the applications that I mentioned, and that's true. So the material space is useful for deriving these priors, and then so then you understand what's happening, and they're basically it's also useful for thinking about what your conservation laws are, right? So basically, if we say, even if we go back to standard optical flow, right? I mean, this brightness constancy assumption, it's based on this implicit notion that there is such a thing as an object point. You know, so this is basically where you say, okay, my object point doesn't change color, right? That's basically a material space statement, right? Because it basically just says there's this abstract notion of a point that I can link to points at different times. So when you actually do these priors, you don't need the material space. Now, sometimes where the material space is actually needed in sometimes, you can actually take one of your time steps and arbitrarily make that your material space, right? So it doesn't need, I mean, the material space could be a very specific configuration in your time sequence. That's also perfectly okay, right? And in other imaging problems, you actually do have, you have a design space, you have something that's deforming, and then you can work with the design space as a reference also. So all of these, depending on the imaging, on the specific imaging setup, you either don't need it, you just grab one of the frames as arbitrarily, or you actually have an actual design space and you use that.
Another follow-up question is, do you think there are particular challenges if we want to have a material space or canonical model?
Okay, so yeah. No, I think that again, I mean, if the imaging problem is something like, I want to understand how a thing that I've engineered and built is deforming over time, right? Which is oftentimes what people in the sciences actually are interested in. They have this thing, they built it according to specs. Now they want to observe how it moves over time. Then you can just choose that design, right? And then basically register everything to that, and that will be perfectly fine. If like in this case of the flower, I mean, I don't have the flower, so I don't have the material space. But basically, if I need a material space, I just take the middle time step or the first time step or whatever. Yeah.
All right. Thank you.
Can you hear me?
Yes.
Okay. So first of all, beautiful results. I have a question about one of the results, the pizza dough result.
Yeah.
There seemed to be, as you play the video, the colors on the outer shell are sort of changing all the time smoothly. I wonder if that's an artifact or.
So there are still, I mean, there are definitely still residual artifacts. However, I mean, basically, this is basically what that. So there is a phenomenon also which. So basically, so there is actually, if you actually look at pizza dough, it's actually interesting. There is like almost like a shell around it. I don't know what actually happens if you actually take your pizza dough, right? Before you knead it again, right? There is actually something like a shell, a thin shell that has slightly different bubble sizes and whatever than what's inside. So we confirmed this with experiments. So it's you know, but I mean, but basically what you see, I mean, of course, a lot of, I mean, there's a lot going on. It's not temporarily that stable. So I think that's a mixture of things just happening. Like these small bubbles, they merge all the time, and that actually happens very, very fast. And I think that those phenomena are also just way beyond the Nyquist limit of the scanning as well. So I think that some residual you know, jitter will be expected, but it's certainly better, and you can better understand it as than if you would just do it independently.
All right, thank you.
Hi, quick question. Great talk. Can you hear me?
Yeah.
Great. So you talked a little bit about deep learning or learning in this context. I was wondering, what is your take about some people in this field are doing system identification of, let's say, I think I see some students from Achuda Katambi's lab, and there's also Steve Bunton, so they're trying to identify the correct model. I'll come over to the front.
Yeah, speak slow because up here I get multiple echoes and they blend into each other, so that's the problem. So yeah, so the question was about basically learning the physical priors. And you know, I think I don't want to dismiss it. I think it's an interesting area for the kinds of things that we look at. Typically, we don't see a huge amount of data. It's very hard to produce good training data. This is even true for something like even just static tomography, right? I mean, you saw me as referring to these optimization problems as basically the state of the art. And I think this is still largely true if you don't know what you're trying to reconstruct. I mean, for everyday scenes, right? We have ImageNet, we have other kind of image databases, and they tend to generalize really well to other large-scale scenes, even with objects that may not be in ImageNet. You know, the networks that we get out, they tend to work fairly well with other types of objects. But you know, in tomography, the object statistics are very different whether you're working in the medical space or whether you're working in material science or whatever, right? You know, whether you analyze fuel cells or whatever, this is all done with tomography. If you go to electron microscopy, you have even other stuff. Yeah. So basically, I'm not aware of anybody who has successfully trained a neural network for doing tomographic reconstruction across the board in all possible kind of application domains. And so that's why these optimization-based methods still win. And when we're talking about motion priors, then it gets even harder to collect the data. And we want to make sure, because it's a scientific application, we want to make sure that it's not just plausible looking, but that it actually somehow we have some confidence in the result as well. And like I said before, I mean, oftentimes, I mean, the reason why we want to image something is because we don't really know in full detail what it will look like. So even synthetic data becomes very tricky, although people for sure are looking into that as well.
Hello, I have a question. Yeah, it feels weird, the echo. Very nice talk. I would like to talk about deformation, and you showed divergence, but what are other means to measure deformation in space-time, like the area element, the volume element, how it is changing? Okay.
So, you know, so the question was about whether there are alternatives ways to characterize the flow field other than just divergence. And so the divergence, so in fact, yes. So I mean, basically the same, if you take the equations that I derived and that I showed you, and you dig a little bit deeper, you very quickly end up with strain sensors, Cauchy strain sensors, etc. If you find it easier to express your constraints and your physical priors in that space, that's also possible. Yeah. So that very much so. Yeah. Okay, should we have another, should we say 10-minute break or 5-minute break? Okay, so thank you very much.
All right, can you hear me? Hello? I don't know how this works. Can you hear me? Hello. Hi, everyone. We'd like to get going with the final part. We're a bit behind schedule, so I'll try to make it for 12:30. But if I don't, then I might be a little bit late. I think we have the room till later, and so you're welcome to stay later after 12:30. Let me just start the Zoom. All right, so we were talking about computational imaging in science. In the first two parts, we've heard Laura talk about the smallest scales, and we just heard Wolfgang talk about imaging dynamic phenomena. So I'm gonna try and talk about the largest scales, so imaging in astronomy, and talk about dynamic phenomena in astronomy, right? So I'll try to tie these two things together. And throughout the talk, I'll try to draw some analogies. As Laura mentioned, there's lots of analogies between microscopy and astronomy. And so we're gonna see some of these throughout the talk. So before I saw Laura's slide, which stated the 1600s for the earliest microscope, I was sure this was probably the first example of computational imaging. Now, granted, I'm taking computational in the very broad sense of the word, but Galileo did not invent the telescope, but he picked up on it pretty quickly, so early 1600s. And here you can see an illustration of his drawing of the shape of the topography of the moon. So he was able to deduce the topography by looking at the shadows. So he had a model of light rays, and he knew where the sun was. And then if you look at that silhouette, then you can pick up topography features from that, right? And today we call it shape from shadows. And this might be an early example of that. At least all the concepts are there except for a computer. Now, when I was preparing for this talk, I had to narrow the talk down because computational imaging in astronomy is way too broad to talk about in 1 hour. There are so many applications. I give here like a really small, interesting set of applications that people are looking at. So in modern astronomy, people are doing computational imaging for all sorts of purpose. Here I show the cosmic microwave background, or exoplanets, or dark matter, and radio astronomy, of course. And today I want to focus this talk on the journey to image the galactic center. Okay, so this is, I'm showing here in the bottom right radio astronomy, and this is how I'll focus my talk, but I'll try to introduce all sorts of computational approaches along the way. Okay, so if you go out to, let's say, the desert or something, and you go to a place that's not very light polluted, you might be able to take a nice picture of the Milky Way galaxy. It will look something like this. And if you look at this at radio wavelength and you start zooming in, you can start zooming in towards the galactic center. That's the journey I want to take you on today. And here you can see a couple of successive zoom ins, and each one reveals different structure. Now, as we move closer to the galactic center, we're going to start seeing this bright radio source at the very center. And if we zoom in even further on this radio source, we can see that it has a structure. It's not just a single pixel, but in fact, it has a shape of a ring or a donut. Now, this image is the first image of Sagittarius A star. That's the bright source, the bright radio source at the center of our galaxy. And this is work of the Event Horizon collaboration, and I will get into this a bit down the line. So in the movies, this type of extreme zoom in is typically just a few clicks by some talented engineers. You have this CSI officer, and the woman says zoom in enhance, and then you have a couple of orders of magnitude of zoom, and all of a sudden you can detect this like something that solves the mystery, right? In reality, or in this reality, all of these successive zoom ins that I showed in one single movie are actually decades of work, and hundreds, if not thousands, of engineers and scientists are working on each of these instruments. And as I said, this last image of Saturday Star is the product of the Event Horizon collaboration, to which Katie Bauman, who's over there, and I'm part of. And this is over 300 scientists working together to get that one single image. Okay, so one thing that makes astronomy very special, or that makes astronomy special, is the heavy constraint that it has by the fact that you have to image through the atmosphere. So any story about imaging in astronomy has to go through this image of atmospheric transmittance or opacity. So what I'm showing here, I'm plotting here, is the opacity of the atmosphere. Wherever you see a window, that means the atmosphere is transparent. And as you can see, the first window you bump into is the visible light. And that would be the window where most life on Earth, including us, have developed to observe. And so it's only natural that this is where the story of astronomy begins. But if you move to longer wavelength, all of a sudden you see this really huge window of radio frequency. And that's where I'll talk about a little bit later on. Now, today we can go spaceborne, and this lets us observe phenomena at all of these other wavelengths that are blocked by the atmosphere. And of course, it's crucial in astronomy to observe different phenomena. Different wavelengths are sensitive to different phenomena, and also observing the same phenomena with different wavelengths will highlight different structures, which can illuminate some of the astrophysics involved. Okay, so transmittance or opacity is not the only problem we have from the atmosphere in astronomy. There's also atmospheric distortions. And so here, if you have an incoming plane wave, and in astronomy, that's the general setting, because everything is so far away, it's always plane waves coming in. And so you have this incoming plane wave, and you have a turbulent layer of the atmosphere. What you get is this distorted wave front. And so you might have seen something like this on a hot day when you're looking at a distance. And in fact, this is the reason stars twinkle. And so the refractive index is the reason, the changes in refractive index are the reason that stars twinkle. So there might be a lot of physics packed into this children's lullaby here. Okay, so one way to overcome this is go spaceborne. And so here I'm showing the Hubble telescope and the newer James Webb Space Telescope, or JWST. And if you go spaceborne, you're not bothered by the atmosphere anymore. And so, and another thing that I want to highlight here, it's obvious that there's a trend in the mirror size. And we can see that bigger is better in this case. And the question is why? And so this goes back to Laura's talk. The reason is diffraction. So when you're in space, you're only limited by, your resolution is only limited by diffraction. And so I'm showing here on the left a slit, which in 2D would be an aperture. And you can see the beam is widening because of diffraction, because these are not rays, they're affected by the finite size of this aperture. And so if the slit starts to be narrower and narrower, we can see a widening of this plane wave. And so this, for a circular aperture, we have this point spread function, again, ties us back to the talk on microscopy, which for could be an airy disk, it could be something more arbitrary than an airy disk. But the resolution, in fact, is limited by the wavelength divided by the diameter of the mirror. So here we can see if we have a bigger diameter mirror, then we'll get better angular resolution, or we're able to observe smaller angular scales. Now, space missions are costly and unpredictable and take a long time. And so it's not like we solved all of our problems by going into space. So here I'm just highlighting the cost, the initial cost of the JWST, and then I'm highlighting all the launch delays that happened, right? So this is a very long process to get to space. And in fact, maybe you've heard on the news that it was hit by a micrometeorite. So this is also an unpredictable, very challenging engineering task. And so we want to have complementary methods or complementary computational methods that can counteract the effect of the atmosphere. And the goal of these methods is mainly to get us to a point where we are as close as possible to the diffraction limit. So in space, we can reach that limit, but on Earth, it's more difficult, but we're trying to do that computationally. Now, I want to talk about these two approaches. Of course, one key thing to overcome the atmospheric distortions would be just go up as high up as possible. And that's why a lot of the times you build telescopes high on mountain peaks. Here I'm showing the Keck telescope, which is on Mauna Kea in Hawaii. And you can see these two laser beams coming out, and I'll talk about this in a second. That's called adaptive optics, and that's an active approach. But there are also very simple passive approaches like lucky imaging. In fact, the concept of lucky imaging is so simple that oftentimes you will see these beautiful images taken by amateur astronomers, in these images called astrophotography, and they can achieve almost diffraction resolution limited imaging just with basic setups. And so I think this is a really cool approach. And so I'll talk a little bit about lucky imaging. So the principle is very simple. And this is a principle that we've seen a lot in computational imaging for photography. Instead of taking this one long exposure image that will be blurred out because we're integrating over all the atmospheric distortions over some integration time, we can take a bunch of short exposure images, and each one will be noisy. So it'll have this kind of speckle pattern. And instead of using all of them, we can just use a small percentage of these frames. Now, we're going to pick the best frames. We're going to have some metric to choose which ones are less distorted. And here, there's all sorts of variations on how to pick them. So I don't want to get into that. But the principle is you pick the best 10, let's say 10% of frames, and then you combine all of them together. And then you can get something that's really sharp and almost reaches the diffraction limit. Now here in the combine, again, there's a bunch of methods. In astronomy, one typical method is called the shift and add. Basically means register all of them to the peak intensity and then add all of them. And this is kind of like image stacking, or what we're doing on our phones on a regular basis. Okay, so now I want to talk a little bit about adaptive optics. And the reason is this is a key technological development in our journey towards the galactic center. And so here I'm showing the Keck Observatory, and I'm showing these stars that are at the center of our galaxy. And you can see that when they added the adaptive optics to Keck, all of a sudden the resolution became really much higher. So beforehand, a lot of these bright stars were actually, you aren't able to see a lot of these dim stars because the bright stars are blurred out to an extent that you can't see them. And so now all of a sudden with adaptive optics, you can resolve many of these stars that you weren't able to do before. And why was that useful? Well, these stars at the galactic center are called the S stars. Here on the right, I'm showing this kind of extreme time lapse. It started back in 1995-ish, and it goes on till today, where astronomers have been tracking these stars and their orbits. And so what we can see here, this is, they've been tracking them in the infrared, and we can see that they're all orbiting around something. And so this thing must be really massive. And in fact, this thing that they're orbiting is invisible in the infrared. So they weren't sure what this could be, but what they know is that it takes something like 4 million solar masses to explain all these stars' orbits. Okay, so just take in the scale of astronomy. I think sometimes I'm really blown away by these scales. There is 4 million times the sun packed into the center of the galaxy, and it's invisible in infrared, just to take that in. And so, in fact, this discovery that there is this massive object that is suspected to be a supermassive black hole received the Nobel Prize for, two astronomers shared the Nobel Prize, Reinhard Genzel and Andrea Ghez. And the AHT image, which I will talk about later, gives us actually the first visual evidence that there might be a black hole in the center of our galaxy. Okay, so before I go into that, let's talk a little bit about this technique that made it possible, adaptive optics. And so, again, going back to Laura's talk, so see how many analogies there are between astronomy and microscopy. We have this incoming wavefront, and it's perturbed or distorted by the refractive index of the atmosphere. And so if we could estimate the wavefront, we could, and in real time, we could deform a mirror. So if we could do that in real time, we might be able to correct for the distortion of the wavefront and get something like the corrected wavefront. And that's the goal of adaptive optics. So the question is, how can we recover in real time the information about the incoming wavefront? So one classical wavefront sensor in astronomy is called the, well, not just in astronomy, it's called the Hartmann shock wavefront sensor, or Shock-Hartmann. And the principle goes as follows. You have this guide star, and again, this is something that's distant. So although it's emitting spherical waves, by the time it reaches the observations, it's going to be plane waves. So you have this incoming plane wavefront. And now, if there's no atmosphere, this incoming wavefront will go through this lenslet array and will be imaged in many individual different points. So each one of these tiny lenslets are going to produce one of these little grid points of the guide star. And if there's no atmosphere, they're going to be evenly spaced. Now, if we have an atmosphere, it introduces a distortion to the wave. And so now we have these local slopes. So the wave is no longer a planar wave. And this, what happens is it hits the lenslet array at different angles. And now the grid on the image sensor is no longer evenly spaced. So we can take that information and recover the wavefront. And so the key advantage here, it's really fast, right? So we can do that in real time, and we can deform the mirror, and this can be done in real time. But the main disadvantage is, A, it has low resolution because we're relying on all of these lenslets. And so we have this grid spacing. We're limited by the number of lenslets we can push onto that. And the other thing is, we can't really recover really big slopes in the wavefront. And that's because these grid points are going to start swapping places, and then we can't resolve that, okay? And to tie us back to microscopy, I think Laura mentioned that briefly, that there's also adaptive optics in microscopy. Now, interesting, in microscopy, you can do adaptive optics in both directions, both in illumination and in recording the outgoing wavefront. So here I'm showing some figure. And on the left, if you want to focus a beam onto a narrow point within a sample, the sample is going to distort that beam just like the atmosphere distorts the incoming wave. And so what you can do is first deform the illumination wave, and in a way that will counteract what the sample is going to do down the line. The other direction, which is more like astronomy, is the outgoing light is also going to get distorted, and so you can deform the mirror to record that light in a corrected fashion. Okay, so back to our story of the galactic center. So we said that the S-stars were crucial to detecting that there's a massive object somewhere in the galactic centers, and and astronomers use those to estimate the mass at 4 million solar masses. Now, on the right, I'm showing the EHT image that was recently revealed, maybe a month ago, of Sagittarius A star. Now, this image assumes no knowledge of a black hole. This is just a radio image, a computational image, but a radio image. And so, zooming out a little bit from the imaging side and looking into the science of these that this can produce, taking in the mass from the S-star orbits, we can plug that into a model, in this case, general relativity, and this will give us a prediction of the event horizon shadow, of the shadow of the black hole. And so I think this is absolutely incredible. These two methods are nothing in common, almost. One of them is in radio, one of them is in infrared, one of them assumes a model of orbit dynamics, one of them assumes none of that, and yet these two converge on almost the same conclusion. So visually, we can extract this, this ring shape from the image, and also we can compute that using a model, and we reach, these two approaches reach almost the same conclusion. Okay, so now I want to talk about the Sagittarius star image and the technology that made that possible, which is radio astronomy. And the story of radio astronomy begins, like many stories in astronomy, by cosmic coincidence. And so here I have Karl Jansky, and he constructed this rotating antenna, which he can rotate around to detect signals. And he did that while he was at Bell Labs for communications back in the early 30s. And when he was recording the signals, all of a sudden he discovered this strong static noise coming from somewhere close to the sun. So initially he suspected that this was the sun. And then later on, using the help of some colleague astronomer, they were able to locate this thing to the center of the galaxy, right? So this was roughly the birth of radio astronomy back in the early 30s. And as you can see, this is already tied in to the story of the galactic center from the very beginning. And so here I have a news article from that time, from the New York Times. And interestingly enough, the news article mentions, it's hard to see here, but it's mentioned in the news article that the source intensity is low. And I think that this is typical for radio astronomy. For radio astronomy, the intensities are very low. You can see the unit that was named after Jansky in his honor, a unit of flux, which has 10 to the minus 26 there, okay? So units in radio astronomy are very low. Okay, so going back to the diffraction limits and angular resolution, let's plug in a couple of numbers and see what we get. So if we look, for example, at the human eye or the Hubble telescope, we can plug in some visible light wavelength. Just for comparison, we plug in 500 nanometers. And then we can plug in some rough sizes of things. So we can plug in 2 millimeters for the iris, or 2.4 meters for the mirror of the Hubble. And we get something like 50 arc seconds and 0.05 arc seconds. Now, arc seconds are an angular measure that it takes some time to get used to people who don't work with it. This is 1/3600 of a degree. So it's already a small unit, and 0.05 is 3 orders of magnitude better than the human eye. Okay, so what do we, if we flip this equation upside down, and I'm gonna give you the resolution of this image of Sagittarius star. The resolution is 20 micro arc seconds. Okay, so micro 10 to the minus 6. So if I plug that in and I plug the radio wavelength and I flip the equation upside down to get what is the rough size of the telescope that can give me this image resolution, what do we get then? We get a telescope of size of 13,000 kilometers. Okay, so that's roughly the diameter of the Earth. And obviously, this is not possible. So we can't construct an Earth-sized telescope. So how did we get to that resolution with the EHT image? So we use a computational approach, which is called very large baseline interferometry. And the key here is that we don't have an Earth-sized telescope, but we can construct many telescopes and spread them across the Earth. Okay, and I'm going to get into how this works. But relying on all of these synchronized telescopes observing the same source in the sky, we can get an effective resolution of an instrument the size of the Earth. It's not the same resolution, but it's an effective resolution. Okay, and this is called very large baseline interferometry. Okay, so let's introduce the basics of interferometry for two telescopes. So if we have two observing telescopes here, and they're observing this distant source, and again, the underlying assumption as usual is it's a very distant source, so we have a plain incoming wave, and also it's monochromatic. And so if we're observing this plane wave arriving at these two telescopes, there's going to be some time delay between the time it reaches one of the telescopes and the time it reaches the red telescope and the blue telescope. And so this time delay will just be this geometrical distance, b dot s, divided by the speed of light, right? So that's going to introduce some phase to the wave coming into the blue telescope. Now in interferometry, we take the signals and we correlate them, which basically means multiply and time average. And so if we multiply and time average these two cosine signals, we get, and we do some trigonometry, we get this summation here. I don't know if you can see my, you can't see it. Okay, so we get this summation here of two cosines. And what we can notice is that the first term is not a function of time. So averaging over time doesn't do anything. The second term, though, oscillates at double the radio frequency. And so if we take any decent integration time, this will go to zero, okay? And so this thing goes to zero, and we're left with just this one cosine that is a function of the baseline, the wavelength, and the observation angle, okay? So again, this is not a function of time. We've averaged over time. Okay, so how does this look like for a source that's moving around the sky? So we have these two telescopes, and let's plug in some numbers for the baseline over the wavelength, and we get something that looks roughly like this cosine function. As the source moves across the sky, we get this oscillating cosine function, okay, that I wrote down at the top. Now, in reality, telescopes are not really sensitive to the entire celestial sphere. Actually, they're very sensitive to their pointing direction. So they have their main lobe, and then everything outside of that main lobe gets heavily attenuated. Okay, so in reality, we're looking at small angles, which are deviations from their pointing direction. And at these small angles, we can approximate the sine theta as just the angle theta. And now we get something that looks just like a cosine function. Okay, so what happens if we have two sources? Now we have A1 and A2. Now, if we have these two sources and we've added another assumption here that they're incoherent, okay, then we get a summation of the emission coming from A1 and multiplied by a cosine of theta 1, and the emission coming from A2 multiplied by a cosine of theta 2. Okay, and the cross terms cancel out because they're incoherent. Now we can see that if we take that into a continuum, this is starting to look like a Fourier transform. So in the continuous setting, this is if we follow the assumptions of the Van Cittret-Zernike theorem, we get that the measurements are the Fourier transform of the continuous emission on the sky. Okay, now the special frequency of the Fourier transform of this two-element interferometer would be b over lambda, meaning that we're effectively sampling at a resolution of lambda over b. Okay, so to contrast that with diffraction limited, we can see that the interferometer resolution is inversely proportional to b, which is the distance between the telescopes, while the single dish limited by diffraction is inversely proportional to the dish size. So this is how you go from a telescope the size of the Earth to just a whole lot of telescopes spanning the Earth. Okay, now, one other thing that the atmosphere does is introduce noise. So in reality, so if this is the ideal measurement, so in radio interferometry, this measurement is called the visibility. And the visibility is this complex number that we measure, again, by correlating the two telescopes. In reality, we have the atmosphere in our way. And so this is going to introduce some random phase, a random delay to each one of these signals, phi1 and phi2. And so we're not measuring this new 1, 2. We're actually measuring this multiplied by a random phase because of the atmosphere above each one of these sites. Now, more than that, we also have different attenuation above each one of these sites. And so this introduces some random gain. Okay, so we have a random phase and a random gain in our measurement. And so how does this look like pictorially for some complex number? So if we have a complex number that has, on the complex plane, it looks like a phase and some vector magnitude. And you can see this would be the ideal measurement. And then if we introduce a random phase, then this is sort of like this is a random rotation in the complex plane. And then if we introduce a random gain, this is some random scaling of that vector. And then overall, if we compare the two, we can see that they don't look at all similar, right? So this is the ideal measurement, that this is what we actually measure due to the atmosphere. And so the question is this all technique lost, and can we still do something? So obviously we can do something, because otherwise I wouldn't be here. And the answer relies on the fact that we don't just have a single pair of telescopes, okay? We have a lot of redundancy by having multiple pairs of telescopes. And so without going much into detail, what we can do is form these closed triangles of telescopes. So we can take the measurements between V1 and between telescope 1 and 2, and telescope 2 and 3, and telescope 3 and 1. This forms a closed triangle. And using all of these measurements, we can see that, for example, V12 and V23 share the same gain error and phase error. And the same thing goes for each one of these other pairs. And so by multiplying together a couple of measurements, we can actually cancel out these error terms and get what's called closure quantities, which are invariant to these random fluctuations. Okay, so again, I didn't go much into details here, but I want to keep going here. Okay, so the other thing is, we talked about how the EHT measures components of the underlying Fourier transform at these frequencies that are proportional to the baseline. In fact, they're not proportional to the baseline, but they're actually proportional to something called the projected baseline. So the projected baseline is not the topographical baseline on the Earth, but it's actually projected onto the line of sight. And so what we can do is, actually, as the Earth rotates, this projected baseline changes. And so notice these red lines, they change they change as the Earth rotates. And that means that as the Earth rotates, we're able to acquire multiple frequencies of the Fourier transform. And so we're starting to fill in the Fourier plane of the underlying image. And this is, again, something that Laura was talking about in the context of microscopy, right? So here in microscopy, they were able to use, they were able to do this aperture synthesis, not because of the Earth rotation, but they changed the direction of illumination. Okay, and so this is kind of analog in the same way, where here we're reliant on the Earth rotation. Now, there is an underlying assumption here. The underlying assumption is that the image that you're looking at is static, right? And as we've learned from Wolfgang, that's not always the case. Sometimes you're looking at something that changes while you're acquiring your measurements. And so for M87, which is the first black hole image that I'm showing here on the right, that assumption was quite good. But that's not the case for Sagittarius A star, which is far more dynamic. In fact, it's dynamic on the time scale of acquisition. And so let me illustrate the challenge here. We have some underlying source. We don't have access to this. And we have this Fourier transform. Here I'm showing the magnitude and the phase. And this would be what the EHT sees. And as you can see, it's hard to see here, but these points are moving in time. And also their underlying value, the color here, is changing because the underlying source is changing in time. Okay, so we have to decouple these two effects to learn something about this source. And the way we do it, the way we did it for Sag star is modeling the measurement as some time average, so some constant component, and some random residual fluctuations. And we assume here that in measurement space, these are Gaussian and they follow some power law here at the bottom. But this is not crucial right now. What I want you to focus on is that we have some model for the statistics of these fluctuations, and it has a couple of knobs and dials that we can change. And if we change these knobs and dials, that would affect the image that we recover. And so as an analogy here, and in fact, these are not the only knobs and dials that we can change. In fact, each one of our algorithms have a bunch of knobs and dials. So for each one of these parameter configurations, we can recover a different image of the underlying source. And here is sort of an analogy in photography. If one image is looking at a very dynamic source and the other one is looking at a static source, and we start messing around with the parameters of the camera, we might be able to snap very different looking pictures for the source on the left, but the source on the right is going to remain constant. Okay, this is just an analogy here. And then we can cluster these images according to how similar they look. And on the right, you can see that all of these clusters look the same. And so that's roughly what we've been doing for Sag star. Here we have, so instead of a single image, actually for each parameter setting, we get a different image, okay? We can play around with these parameters and we're gonna get a different image. And in fact, we had hundreds of thousands of images, and the same thing could be done for M87. Now for Sag star, like the mountain view, you're gonna see that we can cluster them into 4 different clusters that look different, okay? And so we have 3 different clusters of ring and 1 cluster that's a non-ring cluster. And this cluster is roughly 2% of the images, okay? The image that was revealed was actually an average over these hundreds of thousands of images. So you can see that the ring feature is very strong in the reconstructions because it pops out in the average image. Okay, so I talked a little bit about our journey towards the galactic center, and now I want to talk about looking forward into the future to new imaging approaches. Okay, and these are imaging approaches that we've been developing at Caltech towards future EHT campaigns. And so one crazy idea that we had was, what if instead of recovering this image, which is essentially a 2D projection, what if we can recover a 3D evolution of the emission around the black hole over time, right? So this sounds like a little bit like a crazy idea, but bear with me here. And so here I'm showing a simulation or a visualization of how this could look like, right? And so interestingly, as you look at this visualization, you can see that the camera is changing its angle, but it doesn't really matter what angle we have, you're still gonna see a ring, right? And this effect is due to something called gravitational lensing, which is something that we leverage in this work. So what is gravitational lensing? And so just like a lens, gravitational lensing causes the light to bend. And so here I'm showing a black hole in the center of the image. And if we had an emission coming from behind the black hole, it won't be occluded by the black hole because the black hole is gonna literally bend space-time. And so the photons coming from this emission will actually reach the image sensor here on Earth and will create this ring shape. Okay, so what we're seeing here is that emission from all sorts of angles next to the black hole creates this funhouse mirror effect where things get lensed onto the image plane and distorted. And so this was the topic of our work that we were presenting here at CVPR. So if anyone's interested, either come to my poster or just come talk to me after this, and I'm happy to chat about that. And so this is joint work with these great co-authors, yeah. And so I'm going to talk about this in the next couple of slides. I just want to highlight I'm going to highlight some of the connections to what Wolfgang was talking about earlier. Okay, so I'm going to start with the end of the story, which is some simulation results. So again, these are approaches that we're developing for the future of EHE campaigns. And so we're not working on real data just yet, but we are developing this in simulation. And so I'm going to show some results. So here, Sagittarius star occasionally flares up and emits what we think is bright hotspots of emission. So here on the top part, I'm showing some simulated bright hotspots, which are just these compact regions of brighter emission. And as they orbit the black hole, they start shearing out. And this is because of the difference in velocity, in orbital velocity between the inner radii and the outer radii. And on the bottom, I'm showing how this would look like in a synthetic simulation from Earth, if we had access to this. And so this is the gravitationally lensed image that is affected by the black hole gravity. Okay, in reality, we don't have access to this high resolution image. As I said, we only have access to sparse sampling of the Fourier transform of that image. And so here I'm showing 40 minutes of coverage from an extended telescope array. So this is the next generation EHT array where you can, in simulation, add telescopes at potential sites around the world that we are considering, right? So, so if we use these measurements from the NGEHT, we can get something like the reconstructed result on the right, which is quite encouraging that we're able to recover the distribution of these hotspots. Okay, I'll talk a little bit about the key challenges here. And so one key challenge is that we only have access to a single viewpoint from Earth, right? And so if you remember Wolfgang's talk, he was talking about multiple views of a dynamic object. And so here I am coming and talking about a single viewpoint, and I'm trying to reconstruct this dynamic thing. So seemingly it's impossible, but the key here is gravity is such a strong force, and it enforces a really good model on how things evolve over time, right? So in the talk we heard previously, you had these arbitrary, almost arbitrary velocity fields that you had to reconstruct simultaneously. So here we're gonna have a model that is more tightly constrained because of the strong presence of the black hole. Okay, so this is in contrast to standard computed tomography or 3D reconstruction, where you actually use multiple viewpoints. Now, if we didn't have a model, if we tried to reconstruct this frame by frame, we would have a very ambiguous result, because we don't know what happens along each ray, right? Because each pixel is an integration along the ray, there's an ambiguity along these rays. You can replace the emission at any given point and you'll still get the same pixel values. So as I said, to resolve this ambiguity, we have a model that starts off with some 3D emission, a canonical emission if you want, or an initial distribution. And then by plugging in a model for the orbit dynamics, which is enforced by the gravitational physics, we can propagate this over time to get how the 4D evolution would look like. Once we have that, we can do the ray tracing according to the black hole parameters and get a synthetic view from Earth. And the models that we plugged in here are driven by general relativity, which dictates the orbit of mass and photons around the black hole. Okay, so we have a modeled approach for the fluid dynamics here, and we can take the synthetic view from Earth and generate synthetic EHT measurements if we just plug in the Earth rotation and the positions of EHT telescopes. And in the inverse problem that we're solving, we're trying to jointly estimate this initial distribution of emission and this unknown rotation axis. So the underlying assumption here is that the magnitude of velocity is functionally known. Okay, it's a power law with radius. Okay, so a quick overview of how this works. So the first thing is, how do we represent this 3D field? And a traditional approach would be, let's discretize it according to some grid. But we are in CVPR, so we took a different approach, which is using a coordinate-based neural network. Okay, so we borrowed this idea from NERF, and we use this coordinate-based neural network to represent the emission as a continuous function. And so now, how do we fit the model parameters to the measurements? Well, if we look at a single pixel here, then this single pixel can be traced back into the volume, and we integrate over the emission values over all of these coordinates along the array. And so at each coordinate, we query the network and ask, what is the estimated value of emission at this coordinate X? And the network will give us some estimated value, which we can propagate across time using our model for the orbit dynamics. Now we get this emission at point X in time t, and looking at multiple frames and plugging in the EHT sampling over time, we can get the model predictions to what the EHT will see at our current estimate. And so comparing this to what the EHT actually sees, or in this case in simulation, we can supervise the signal with gradient descent because everything is differentiable, and propagate the gradients all the way to the network parameters and the unknown rotation axis. So one key thing of this approach is that in principle, it can recover arbitrary emission distributions. And so we don't have to have a model distribution of emission. And here we want to illustrate that by recovering these three-dimensional digits orbiting in space. So I'm showing on the left just how this looks like from different viewpoints. Again, in reality, we will have access to just one viewpoint, which I'm showing on the right, how these digits are smeared out over the course of the orbit. So they form like these hotspots and then smear out. And here I'm showing the reconstruction as a function of measurement sparsity. And the interesting thing is that if you look closely at the NGHT recovery, the NGHT recovery is in the center there. You can see that we're able to recover the features of the tube, which actually forms behind the black hole. And by the time it reaches the front, it's already been sheared out. So that's interesting. And we're hopeful that we can use this approach in the future. Okay, so as a last note, everything I showed here in the last part of the talk has been first steps. So this has all been in simulation, but we do have these encouraging results that are getting people within the EHT and the astronomical community excited about this. So the NGHT is not just an array of telescopes, it's also a collaboration of members working towards a scientific goal. And I think this is a really nice thing about, this work is that we're not following a traditional paradigm here where you have this science goals, which dictate the building of the instruments, which then followed up by algorithm development. I think here we're really getting the ability to simulate instruments really gives us this new capability where we can flip this script and generate something like image-driven science. So here we're showing a new imaging capability, and this is actually changing the agenda of the science goals, which can impact down the line the instrumentation design. And this is something that we're really excited about. I think this was my final slide, so I'm happy to take questions. I didn't plan this question.
Can you hear me?
Yeah.
Okay. There's a try to.
Oh, I can.
Can you hear me?
I can hear you, but I can't understand because the echoes.
So you have a slide showing basically that if you have Earth-sized telescope, you to see central galaxy. And then you said, well, effectively we have something similar. Question is, why is the image still so photosensitive? I mean, if you have a Earth-based telescope in that analogy, should you see where image with higher frequencies?
Yeah. Did I need to repeat the question, or did other people hear it? Okay, they heard it. Okay, so the answer is twofold. First, if you had an Earth-sized telescope, you will be able to resolve this image at the same resolution. But if you remember the multiple 100,000 images that I showed that we reconstructed, those are based on all sorts of prior assumptions of our algorithm. So instead of all of these, you'll just get one single image at that resolution, okay? And the answer about this being oh, you can't see this. Oh. Yeah, okay, so that was half of the answer. The other part of the answer is the resolution of this image is 20 microarcseconds. And again, a microarcsecond is 1/3600 of a degree. And a microarcsecond, so this resolution is equivalent to seeing the details of an orange on the moon. Okay, so it's the most high resolution astronomical image ever generated. And so the reason that this is still blurry is because it is so far away. It's ridiculously far away. It's 25,000 light years away. And so even with an Earth-sized telescope, this is still the expected resolution according to the diffraction limit. You just won't have any ambiguity that we have using computational imaging.
So we follow up. So you're saying that basically you have an Earth-sized telescope, you do not expect to see something as crisp as the simulation.
No, yes, I would not expect to see that. But if you had this kind of telescope, you could do other things. For example, a lot of our uncertain, so this image is blurred further than the nominal resolution of the instrument because it's an average of 100,000 images, right? And so you won't have that anymore. So now you can start looking into the variability of the source with more confidence, right? And so you could do a lot of other stuff, but you still won't see some of the really crisp, wispy structure with this size telescope. You might see some of them, but probably not as high resolution as what I showed before. I think this is below the nominal resolution, or higher than the nominal. Yeah, that's a really good question. So first I want to highlight some of the differences between the second part of the talk and the first part of the talk. So when I talked about the Sagittarius star image, I highlighted that we didn't have any assumption that there's a black hole there. When I talked about the tomographic reconstruction, by design, we assumed that there's a black hole. And now we're trying to look at different physics, which is the physics of the hotspots. Now, what we know is that Sagittarius star flares. So if you look at the overall flux, so if you won't have the image structure, but just the overall intensity coming from the center of the galaxy, you can see all of a sudden these flares coming up, sometimes even several times a day. And if we're lucky enough, we might observe them with the EHT telescope. And there are physical models to what explains these hotspots. For example, they're not very dissimilar to solar flares that you might be more familiar with. There's something called magnetic reconnection where magnetic lines are formed and then they reconnect and there's a burst of energy. But again, this is exactly what we're trying to inform. These are the models that we're trying to inform because there's a lot of uncertainty to how these things happen and why. And so this is where this type of imaging could be useful to understand these hotspots, how they originate and what happens to them and what creates them. Yeah, that's a good question. So not only does it reduce the number of measurements, it also makes our measurements nonlinear. So instead of just having a simple Fourier transform, now when we multiply the couple of measurements together, this is not linear anymore. And this introduces correlated noise. And so it has a lot of disadvantages, but it has a clear advantage. And in reality, we use this in conjunction with something that's called self-calibration. And so we can alternate two optimization methods between solving for an image and solving for the unknown quantities here. And yes, the answer is yes, we did use closure quantities for the actual Sagittarius star image. It has problems with it, but it also has big advantages. I couldn't hear you, but yeah, I think I understand from the hand movement.
Hi, thank you for the talk. Ask you whether we can assume that simulations are accurate, and if so, is there anything that stops you from training for these simulations? And then assume that the images are some images that's in EHD and redraw.
I kind of partially heard the second part. I missed the first one. Maybe you can come over here. Yeah, sorry about that. It's, you can hear from the stage, but I think because of the way the speakers are pointed, yeah, you only hear the echo. Yeah, okay, good question. So the question is, how much accurate is the fluid dynamic simulation? Can we train on it as priors on how things evolve over time and recover this that way? Yeah, I think this is a good question. I think this is one of the things that you have to really carefully weigh and balance out. I think Wolfgang talked about it. I asked him a similar question. And so for scientific applications, oftentimes we want to inform these exact simulations. So for example, we have fluid dynamic. In fact, these high fidelity simulations are called general relativistic magnetohydrodynamics. That's a mouthful. And we have these simulations, but astrophysicists are unsure about a lot of them. Okay, they have two different models. They're not sure how the magnetics behave, and they're not sure about many things about these simulations. So in reality, we want imaging to inform these simulations. So we want to have them as unbiased as possible by this prior simulation, I guess. We're still biasing them using some models. So here, for example, in the NERF example, I bias them using the fact that I rely on general relativity. But you have to carefully weigh in which model are you actually examining with your imaging, right? And so I used one model as a bias or a prior, but I wanted to learn about the plasma physics that's happening. So I don't want to use both models in this way. If there are no further questions, so I will close out the session. I just wanted to thank people for coming. I hope we were able to communicate all these connections across these different scientific disciplines. I think it's quite remarkable how interconnected microscopy, astronomy, and the dynamic imaging work that Wolfgang was showing are. And so you can see across the boards, these ideas can hop over from one field to the other and be used in many scientific applications. So thank you all for coming, and we'll see you around at the conference.